Now, you might walk into your closet sometimes and you're looking at 5 items, 2 pairs of pants, 3 different pairs of shirts, and you might go, gosh, I have nothing to wear. But the truth is, you can actually come up with a collection of different outfits when you have 2 pairs of pants and 3 different shirts. How many outfits could you create? Our goal today is I can construct a sample space for a given experiment and determine which members of the sample space are related to certain events. How many different outfits can I make? Well, first of all, we have to recognize that we have 2 different choices here. We have a choice that refers to t-shirts and we have a choice that refers to pants. So let's start with the t-shirt choice. I had 3 different options, right? Now I can pair each one of those options with my pants. And there were 2 pant options for each. So an outfit could be a black shirt, black pant, black shirt and jeans, brown shirt, black pants, brown shirt and jeans, white shirt and black pants, white shirt and jeans. So how many different outfits can I make? 6. At this time, make sure you have your Unit 8 sample space notes out next to you. We're going to start with some vocab. An outcome is the result of an action. So for example, my action was pairing these choices together. The result of that is I get these different outcomes. Sample space is a list of all possible outcomes. So this is the sample space you see in front of you. There are 6 outcomes for this event of my shirt choices and my pants choice. A tree diagram, also what you see in front of you, it's a way to show all the outcomes. It's really important to recognize that on a tree diagram, just like on trees, you have branches and those branches lead to different areas. So you read a tree diagram by following the branches. Let me explain. The branches lead you to specific outcomes. So for example, black shirt, black pants, that is an outfit. And I get that by following the branches. Let's move to chunk 2 in our notes where we're going to focus on creating and reading a sample space. So here is that tree diagram, except this time it doesn't have pictures, right? It's the exact same event though of picking an outfit when you have 3 different shirts and 2 different pant options. So you'll see the word start in chunk 2. And then go ahead and put this tree diagram in your notes. Now this is not the only way to show how many outcomes there are when you have 3 different options for the first choice and 2 different options for the second choice. You can also show it using a table. So you can see that on the top you have my second choice, which was pants. And on the side here, you have the first choice, which was a shirt. And you can see that I have each option there. So I could do a black shirt, black pants, that's 1 outcome. I could do black shirt, jeans, that's another outcome. So these sample spaces both illustrate the exact same thing, except they're showing it differently. One is a tree diagram, one is a table. Will you go ahead and fill in this information in your notes on the blank chart provided in chunk 2? So now, like we were reminded up top, I know tree diagrams are not new. We read a tree diagram by following the branches. You don't have to start a tree diagram with the word start. I just find it helpful. And also you can put tree diagrams going from side to side like this one, or even top to bottom. But looking at this tree diagram, what's the total number of outfits? 6. Remember, we read a tree diagram by following the branches. So 1 outcome again is a black shirt, black pants. But you might go, Ms. Kluger, I don't see black shirt, black pants at the end here, like you had on this one, right? It paired the 2 choices together for the final outcome. Well, but if you follow the branches, you'll see that this whole branch is an outcome. This whole branch is an outcome. So we can end up just counting these back ones here, but recognizing that 1 outcome is not just black pants. It has to be paired with the first choice, which was the black shirt. So we have 1, 2, 3, 4, 5, 6. And we already knew that. And you can also see that in the chart right here. 1, 2, 3, 4, 5, 6. So there is a total of 6 outfits that I can make. That means there's 6 total outcomes. Go ahead and fill that in the blank. That is part of the bottom of the second chunk in your notes. So a rectangle shape in a set of blocks comes in 2 sizes, small and large, 3 colors, yellow, red, and blue, and 2 thicknesses, thick and thin. Draw a tree diagram to find the total number of outcomes. So we are constructing a sample space to see how many different options we have for this rectangular shape that comes in a set of blocks. So let's just start by writing the word start. Sometimes that's helpful. Let's look at our first choice, which is size, right? How many size options do I have? 2. That's how many branches I'm going to draw out from the word start. One of the options for size is small. The second option is large. Do you see why I drew 2 branches? Because that's how many options I had for that first choice. My second choice is 3 colors, and how many options do I have for colors? 3. I could get yellow, red, or blue. Well, I need to pair each one of these options with the first choice. Under the first choice here was small, how many branches am I going to come out given my second choice? 3, because there are 3 options in my second choice. Given my first choice, if it's large, how many options are there for the second choice? 3 still. So what I'm going to have you do here is I'm going to have you finish this tree diagram and then come back and check your tree diagram with mine. So you still need to fill in what the different options are for colors, and then you have another choice with this rectangular shape. It's thickness. And how many options do you have for thickness? 2. So think of how many branches you're going to have coming off from each one of the colors here. You'll also notice in this tree diagram, 6th graders, that I'm going from top to bottom. Is that okay? Yeah. One final thing that you're going to notice that's different about this tree diagram, I'm abbreviating the different pieces, and that's okay. You don't have to write out the word small, you can abbreviate it. All right, pause the video here, finish this tree diagram, then come back and compare mine with yours. Here is my final tree diagram, 6th graders. And when I'm looking at it, I can see I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 total outcomes. So you make sure in the chunk in your notes that you write that there are 12 total outcomes on the line provided, because that was our job with this problem, to draw a tree diagram to find the total number of outcomes. Now, do you see how I counted the thick, thin to get my 12? You can do that. You can count the bottom piece right here, but please recognize that one outcome is not thick. It's small, yellow, thick. So it is nice, if you're not comfortable with tree diagrams at the beginning, to create a final outcome branch, which I did for these 2 right here, where you can see this whole thing is one outcome. It's not just the thin, it's the small yellow thin. So remember, you read a tree diagram by following the branches. So you have to take all the choices within the branch path, and that makes one complete outcome. You might ask the question, do I have to draw a tree diagram or a chart or make lists of all the possible combination of outcomes in order to figure out how many total combinations there are? No, there is a faster way to figure out a sample space size, and it's called the counting principle. However, the counting principle isn't going to give you insight into specific outcomes. For example, with our rectangular shape, what if we wanted to figure out how many outcomes will include red? The counting principle is not going to tell you that. It's just going to tell you that there are 12 total outcomes in this experiment. Before I show you how to use the counting principle, go ahead and go to the first chunk in your notes and read the definition of counting principle. If there are so many ways of making one choice, followed by so many ways of making a second choice, and so on, because we could have more than 2 choices in an experiment, counting principle says you can multiply the ways or number of ways for each one of those choices, and you're going to get the total number of outcomes. So let's do that right now with our rectangular shape experiment. We already know that we should get 12 total outcomes, right? Our tree diagram showed that. So let's start by identifying our choices. Our first choice in this experiment was size. Whenever we're doing the counting principle, I think it's really beneficial to draw blanks to represent the choices. So that blank below represents the choice size. What was another choice? Colors. So draw another blank for that. And then the last choice, thicknesses. So draw a blank for that. Counting principle says you can multiply all the different ways to make these different choices, and you're going to get the total number of outcomes. That can kind of be confusing, so I like to break it down with specific words. How many options are there for choice 1? Small and large, that's 2 options. For choice 2, how many options are there? 3, yellow, red, and blue. And for choice 3, how many options were there? Well, you could get thick or thin. You got it. So if we multiply these numbers together, 2 times 3 is 6, times 2 is 12. You can see that we get 12 total outcomes. And that's what our tree diagram showed as well. So the counting principle is a really fast way to figure out the total sample space. However, this right here doesn't really help us out with figuring out specific outcomes. For example, what if I wanted to know how many outcomes will include blue in this experiment? Does the counting principle tell you that? No. So the counting principle isn't helpful when we're looking for specific outcomes. However, it is extremely helpful to get the total number of outcomes rather quickly.